Okay, guys, I decided to go over number 14.37. It is almost identical to what you'll need to do in 14.36 and 14.38. And these were really commonly missed problems on the homework. Okay, so this is rate laws, chapter 14. So clear equilibrium out of your head. You're going to consider the gas phase reaction between nitric oxide and bromine, and you're given the following data. So the first one is to determine the rate law. So when you're given concentrations and initial rates, you'll need to compare to decide if it's zero, first, or second order. So I'm going to start by writing out my rate law. Rate is equal to K times the concentration of my reactants. Now I'm going to leave room to put in the order of my reaction. So for my NO, I'm going to choose one that changes, and the Br2 is held constant. So I'm going to choose these. And to go from the top to the bottom, this is times 2.5. When we look at the rates, 150 divided by 24 is 6.25. So what we need to do is realize that 2.5 squared equals 6.25. That tells us that we need to square our data, which is a second order. So I can put that up on my NO. A lot of people miss this step. They also miss this step in 14.34. So be aware of that. Second, I want to look at my Br2. So I want to look at one where my NO is held constant. So 0.5 divided by 0.2 is 2.5. And when I look at my rates are also 2.5. So if it's a direct relationship, then it's a first order. We don't actually have to write that in, but I will for our purposes here. Next, it says to calculate the average value of the rate constant for the appearance of NOBR from the 4 data sets. Now, notice the data that we're given here is for the appearance of NOBR. That's important, and I think a lot of us missed that in the directions. It also says to calculate an average, which means that we need to do it more than once. So I'm going to rearrange my equation so that K, which is what I'm looking for, my rate constant, is equal to the rate divided by the concentration of my NO squared times my Br2. Now, I need to do this for reaction 1, reaction 2, reaction 3, and reaction 4. You're going to get really similar values, but they're not all going to be the same. So remember, in order to do an average, you have to have numbers to average. A lot of you only did 1, and that's not accurate. I'm just going to show you how to do 1, and I'll give you the values for the other ones. So to find it for the first reaction, I'm going to take my rate of 24 over my NO value squared times my Br value. And for K1, I get 12,000. Now, we need a unit. This is a third order overall. So it's going to be 1 over m squared s. Now, when I do this, I actually find out that all of my K values are the same for this one, but you still needed to work it out. That is not going to be true for number 36 and 38. Okay, so you're going to work all those out. Add them up, divide by 4, and we're going to find that our K is our 12,000. Again, it works out in this one that they're all the same. The other ones, 36 and 38, are not exactly the same, so you need to take that into consideration. Now, C says, how is the rate of appearance of NOBR related to the rate of disappearance of Br2? This is where some of us kind of lost it. So, to write this, I need to use my comparison of rate laws. And so for that, I need to look at my equation. So I'm comparing my NOBR and my Br2. They don't have the same coefficient stoichiometry-wise. So I'm going to say that for every 1/2 of my change in concentration of NOBR over change in time, that is equal to just a complete loss of my BR2 over time. Remember, negative here because it's a reactant, so it's disappearing throughout the reaction. So this is just my comparison, but now I want to use this and I want to find what is the rate of disappearance of BR2 when my NO equals 0.075 and my BR2 is 0.25. Now, I calculated my K value for the appearance of NOBR. So when I plug my values in to my rate law, I'm going to find my rate of NOBR. But we just determined that those values here and here are not one-to-one. So I'm going to start by putting my data into my rate law. So rate is equal to my K value, which I found was 12,000, times, I'm going back up to my original rate law, my black one up at the top, my concentration of NO, which is 0.075 squared, times my concentration of BR2, 0.25. When I do that, I find that my rate is equal to 16.875 molar per second. Now, I used my rate law for the appearance of NOBR. So that means that my rate of appearance of NOBR is 16.875. However, we found in our comparison that half of the rate of NOBR is what our BR2 is. So before I can call this my final answer, I need to take my rate divided by 2, and I end up with 8.44 molar per second for my BR2. Again, you guys, this is really, really similar to what you're going to find on numbers 36 and 38. So please take a look, go back, make any changes. You'll have to do a problem like this on your test. Come tomorrow with any questions.